Hey everyone, welcome back to another OneClass session. My name is Bassam, I'm an engineering graduate, and today we're going to be going through some physics problems. These will be at the high school and preliminary university level. So let's get started over here with the first question. So the first question we're given is, in order to get an object moving, you must push harder on it than it pushes back on you. Is it true or false? Explain. So this is kind of asking a question about Newton's third law of motion. So Newton's third law of motion is for every action force oh, just give me a second here. You guys can see what I'm writing. All right, just give me 1 second. Let me just fix this quickly. Okay. So for every action force, there is an equal and opposite. So those are the two key words, equal and opposite reaction force. And that's Newton's third law. So knowing this, the question is asking, in order to get an object moving, you must push harder on it than it pushes back. That would never be the case. The amount of force you apply to the object will apply an equal and opposite force to your action. So if the object was, like, let's say, a box on the ground somewhere, and if I was pushing the object with some applied force Fa, the object would push back with the same applied force but in the opposite direction. So I'm pushing on the object with Fa, and the object is pushing back with Fa. So let's look at the attempted solution. When an object is pushed by a force, its motion is dependent on several factors. It depends on the normal force of the object opposite to the direction of applied force, the weight of the object, the friction force acting with respect to the ground, the angle, etc. Hence, this statement is false. Only pushing harder will counter the normal reaction, but the rest of the parameters are still left to move the object. This statement is false. Opposite. So this is a correct answer, but incorrect explanation. So correct answer, false. The explanation should have to do with Newton's third law. Newton's third law of motion states that for every action force there is an equal and opposite reaction force. So correct answer, wrong explanation. Okay, let's go to the next question now. So we'll clear the page here. Doesn't seem to be updating too quickly. Okay, so next question. if light strikes the first mirror at an angle of theta 1, what is the reflected angle of theta 2? Okay, so this question is kind of telling us that we have some mirror with an incident angle, and we want to know kind of what does the reflected angle. So if we think of just kind of a mirror like this, so we'll say this is the mirror, and light is coming in from this side. So usually we measure the angle from the normal line to the mirror. So this would be theta 1. And then we have the reflected angle over here, theta 2. So the law for this is essentially the incident angle will equal the reflected angle. So here theta 1 will equal theta 2. The only time the angle changes is when the angle is refracted through a medium. So here the attempted solution is the reflected angle theta 2 will be the same as the incident angle theta 1 as compared to the normal line that is perpendicular to the point of incidence of the light ray with the mirror. The normal splits the total angle by the incident ray and the reflected ray. So this is the correct explanation, and we can see that the incident angle, which is theta 1 in this case, will be equal to theta 2, which is the reflected angle. So, correct answer. Great job. Okay, let's get to the next question. All right, so the next question, why do clothes often cling together after tumbling in a clothes dryer? So this question is essentially asking us, when things rub together in the dryer, what is going on and why are they clinging together? So whenever we have kind of two objects, regardless of what they are, so here, if there's two objects, let's say this is a piece of clothing and another piece of clothing, and they're rubbing against each other, then we have electrons on both. I'll just represent these by negative signs. And what's happening is electrons are just moving from one piece of clothes to the other. So we'll end up with, maybe we'll take away these two electrons and we'll put them over here. So now we have a more negative charge on this piece of clothing and a more positive charge. So because electrons are being removed, we know that it will become the more positive. So there's no positive atoms that are moving around, it's just the electrons moving around. So because positive and negative charges attract, that's why you get the attraction between the two pieces of clothing. And then the name for this is the Triboelectric Effect. And this is just the fancy name of when two kind of objects rub together, electrons are moving between them. And this is more to two insulators rubbing together. So the clothes here act as insulators rubbing together, and then the electrons are moving between the two pieces of clothing, causing a positive and negative charge to each piece of clothing, and then that causes the attractive forces between them, and then they start clinging together. So here, the attempted answer is when clothes are dried in a dryer, clothes get rubbed together and the electrons on the outermost layer of clothes pass to other attached clothes and get charged. Thus the charge on clothes gets accumulated and adhesive force acts on clothes. Hence rubbing the clothes made the clothes charge and the clothes cling together when dried in a dryer. So it's the movement of electrons and the charges that accumulate that causes. So this is the correct response. Okay, let's go to the next question. Okay, so the next question, if Earth were twice as far from the Sun, the force of gravity attracting Earth to the Sun would be what? So here it's looking for the um, force of gravity or force of gravity between the Sun and the Earth, and we use the gravitational equation, so which is represented as follows: Fg equals g, that's the gravitational constant, times the mass of the Sun times the mass of the Earth, over r squared, which is just the distance between the Earth and the Sun. So here they're not giving us these values. So essentially, we in this scenario, it should probably, the question should give us values. So I'm just going to look at the answer. Oh, actually, what is, if Earth were, oh, so here it's saying if Earth were twice as far from the Sun. So it's asking us if Earth is twice as far, the force of gravity attracting Earth to the Sun would be, okay, so we're trying to think of if it's bigger or smaller. So sorry, I misunderstood the question. So since r here in our equation represents the distance, that's what we're kind of looking at. So we have r squared in the denominator. So if we doubled r, so if we made r 2r, we would get 2r squared. And 2r squared is just equal to 4r squared. So knowing this, we can kind of see how that relates to the force of gravity. So we're trying to figure out how does this affect Fg. And since we have Fg on this side, and then we have r squared in the denominator, we know that they're inversely proportional. So we know Fg is inversely proportional to 1 over r squared. So we know if r is increased, that means Fg should decrease. And in this scenario, because the 2 turns into a 4 and we have the squared component, we know if we double the distance, that means we end up with a 4 in the denominator. That means the force of gravity would decrease by 4 times, or by a quarter of what it originally was. So we'd have Fg to 1 over 4 of what, if when we're comparing the regular distance to the distance increased by double. So that's kind of our answer here. So here, as we know, the force of gravity between two masses is directly proportional to the product of the masses, so they have the correct equation, and then they substitute 2r double, and they get 4. So you can see that the new force of gravity between the Earth and the Sun becomes a quarter of what it originally was because of the component in the denominator. So this is the correct attempt, so correct solution. So great work. Okay, let's go to the next question. Okay, so here we have a fill in the blank question. So I just want to double check that this is working. Okay, let me just. So the blank is a plane perpendicular to the optic axis through the focal point. So if we think about kind of just a lens diagram, so if we had some lens and we have the center axis like so, we're trying to think of what plane is a plane perpendicular to the optic axis. So the optic axis is just this line that I drew. It goes through the center of the lens, and it's actually asking us at the focal point. So the focal point could be somewhere over here, and we're wondering what is the name of the plane of that that is perpendicular to the optic axis and the it goes through the focal point. So essentially some axis through here, or some plane through here. So we'll label this as optic axis, and then this is our focal plane. Focal because it goes through the focal point. So that's the answer we're looking for. So the focal plane is a plane perpendicular to the optic axis, so we can see that here. The two are perpendicular to one another through the focal point, and it goes through the focal point. So let's look at the attempted answer. In optics, the measurement of the distance of the object and the image is measured on the optic axis, also known as the principal axis. So that's two names for the optic axis. So it can also be called the principal axis. The optical device is kept at the origin of the optic axis, and the focal point lies on this plane. A focal point has a plane perpendicular to the optic axis known as the focal plane. So this is the correct answer. Okay, and we'll mark this as correct. Okay, going to the next question. Okay, so I'm going to have to replug this in. What is the magnitude of the gravitational force acting on the Earth due to the Sun? So this is the question that we have to use kind of the gravitational force equation. So it goes as follows: Fg equals G mass 1 mass 2 divided by r squared. So for any two masses, there's a gravitational force. What is the magnitude of the gravitational force acting on the Earth due to the Sun? So they don't give us any values, but we'll look at the answer here for the values. So the gravitational constant is right over here, 6.67 times 10 to the negative 11. And then we have the mass of the Sun, 2 times 10 to the 30. And then we have mass of the Earth, 6 times 10 to the 24. And then distance is 1.5 times 10 to the 11 meters. So we can essentially sub all these values into the equation up here. So if we sub in for G, 6.6, here let me actually make some space. So we'll start over here. So we have 6.674 times 10 to the negative 11 times the first mass, which is the mass of the Sun, 2 times 10 to the 30, times the second mass, which is the mass of the Earth, 6 times 10 to the 24, divided by r squared, so the distance between the Sun and the Earth, which is 1.5 times 10 to the 11. And we'll plug this into our calculator. So 6.74 times 10 to the negative 11, 2 times 10 to the 30, 6 times 10 to the 24, divided by 1.5 times 10 to the 11. And we end up with 5.3, so I might have plugged it in incorrectly. So 10 to the 11, to the 30, 24, to 11. Oh, so I forgot the squared over here. Okay, so we should get 3.56 times 10 to the 22 newtons. And that's our final answer. So in the attempted solution, they get 3.52. So this is probably due to just an approximation error, but the process and the final answer is close enough, so we'll mark that as correct. So correct answer, great job. Okay, so the next question is asking about bromine. So bromine has two naturally occurring isotopes, Br79. Let's go write that down over here. So this is more of a chemistry question because we're looking at kind of how bromine relates to the periodic table, but we'll go through this. So Br79, so there's two isotopes of bromine, and then Br81. And then 79 and 81 just refers to the atomic mass. And then the atomic mass of bromine, so the average based on how much of each element occurs naturally, is 79.904 AMU. Okay, and then we're given the mass of bromine 81 is 80.6163. So actually, I'll move this down. I'll move this up here so we know this. And then so mass for bromine 79 is not given, but mass for bromine 81 is 80.9163 AMU. And then we have its natural abundance at 49.31%. And we need to calculate the mass and natural abundance of bromine 79. So because we know there's two isotopes, we know that the total abundance needs to equal 100%. So to find the abundance of bromine 79, we just take 100%, subtract it from 49.31, and we'll end up, so I'll write percent. So we should get 50.69%. Let me just double check the math. 100 minus 49.31. So yeah, 50.69%. So we know that's the abundance of bromine. Now we have to calculate the mass. Because we know that the mass, the total mass up here, should be kind of the weighted average of each isotope of bromine. So we can kind of write an equation below. So if we had 79.904 should equal, let's represent m by x. So the variable x times 50.69%. So we'll write that as a decimal place. So 0.5069 plus the mass of bromine 81, which is 80.6163. 9163, and we multiply that by the percentage, 49.31. So we'll have 9163 times the percentage, which here is 49. 49. Yeah. So we would write multiplied by here. I'll actually move this down here so it's a little more clear. So I have a little more space, so it'll be plus. And then we're going to multiply this by 0.4931. So now all we have to do is solve for x. So we'll rearrange. So we'll get a master equation. So if we had 79.904, we'll subtract this from both sides. And we'll get minus 80.9163 times 0.4931, and then on the right side we would just be left with this, so we'll divide by that. And divided by 0.5069, and that should equal x. So moving above, so here we can just kind of plug this into our calculator and we will get, so 79.904 minus 80.9163 times 0.4931 divided by 0.5069. We end up with 78 0.919. Let's go 4 decimal places because that's how we should actually probably just use 3. We'll just leave 3 decimal points. So here we have the mass of bromine 79. 79, is that correct? Yeah, 79 is 78.919. And the abundance is 50.69. So let's look at the answer here. Returning the mass. So it looks like the attempted solution is just giving the process, not necessarily the final answer. So here we'll say correct process, no solution present. So mass equals 78.919 AMU, and abundance equals 50.69%. Okay. Let's go on to the next question. Okay, so here we're asked the following. The picture shows a motion diagram. The dots represent the object's position at moments separated by equal intervals of time. Okay, sorry, just give me a second. The dots are connected by arrows representing the object's average velocity during the corresponding time interval. Which of these situations describe the motion shown in the motion diagram at point A? So it's giving us a bunch of scenarios. Oh, here's the diagram. And we're looking at point A here. So it's giving us some object that's moving along and it drops down. So here we can think of it as kind of the position diagram over time. And then between each object, so we can kind of draw a plot over here. So we can think of the x-axis. Let's just read double check the question. The dots are connected by arrows representing the object's average velocity during the corresponding time intervals. So yeah, the average velocity between the time intervals. So between this point and this point, you have the same time interval. Between this point and this point, you have the same time interval, and so on. And then you have different velocity vectors between each point. So we can think of it as the well, here it's kind of just showing us a position diagram, so we can't really represent it in an XY coordinate diagram. So we'll just use this image. We'll go through the options. So we have a car is moving along a straight road at a constant speed. So this is question number 8. Okay, so it's not showing up here for you guys. Okay, all right, it should be a little better. All right, so we have question 8. So option A, we're thinking about option A. A car is moving along a straight road in constant speed. So we'll look back at the diagram. So we can see before A and after A, the velocity vector is the same. So we know it's constant speed here. There's no acceleration. So A looks like it's correct. So we'll look at the other options too, but based on here, in A we have the same vector before and after, so we know it's, there's no change in speed, it's the same speed. In B, you can see the vector gets shorter, so there's a kind of a deceleration. And then at point C, you can see that before and after, the vector gets longer, so we know at point C there's an acceleration. But at A, it's just constant speed. So we're kind of looking at options that have constant speed. So for B, A car is moving along a straight road while slowing down. So we know because it says slowing down that B is incorrect. But for some reason, this is not loading. Okay, there we go. And then for C, a car is moving along a straight road while speeding up. So once again, because it says speeding up, we know we're looking for constant speed, so this is also incorrect. Let's look at option D. A hockey puck slides along a smooth, frictionless, icy surface. So because there's no friction, that means there's no deceleration. That's essentially what this option is telling us. Therefore, if it's moving smooth along an icy surface, we know that no friction means no deceleration, and we have constant speed. So D is also correct. So we have E. A hockey puck slides along a rough concrete surface. So because it says rough concrete surface, that means it's going to slow down and we don't have constant speed. So we'll mark that as a no. Then we have F. A cockroach is speeding up from rest. So acceleration, that's not constant speed. We have G. A rock is thrown horizontally. Air resistance is negligible. So if we think about this one, in the horizontal direction, there will be no acceleration, but because we're throwing any rock horizontally, the force of gravity will be acting upon it downward, so it'll eventually slowly be falling down. And that's not really what our diagram is showing. It's showing that at point A, there's constant acceleration in kind of the x direction, so this would not be the case here. There's no y deceleration or acceleration downward due to gravity. So G is incorrect. H is a rock is thrown horizontally. Air resistance is substantial. So air resistance doesn't matter because the force of gravity is acting upon it. So here in air resistance just causes more friction to slow down the object, but we don't have constant velocity. So H is incorrect. Look at I. A rock is dropped vertically. Air resistance is negligible. So same idea, and then J, same idea. So because of the force of gravity, we have acceleration and it's not constant speed. So we have D and A. That's the correct answers. So here, let's look at the attempted solution. Solution A and D. Reason in a velocity of a car. Sorry, just the grammar is off here. Velocity and D. Okay, so they just describe why A and D is correct, and they have the correct explanation. So, correct answer. Great job. All right, let's go on to the next question. Okay, so when a light beam emerges from water into air, the average light speed does something. So we're moving through two mediums. One is water and then the other is air. So let's say we had one medium. We'll say this is, oh, it's not showing up here. Let me just unplug and replug back in. Just give me a second here. Okay, so the main idea here is that we're looking at the index of refraction and kind of the speeds in two mediums. So we'll say this is, so we'll start with water. Let's say there's from water into air. So this is, let me just review this. So we have water, air, and then we have some light beam like this. And we're going from two kind of indexes of refraction for each one. So air has some index of refraction NA, and water has some index of refraction NW. And then the equation that is used to determine the speed is V equals C. So C represents the speed of light in a vacuum, which is just 3 times 10 to the 8 meters per second, over N, so the index of refraction. So for air, air's index of refraction is pretty close to 1. It's 1.00 something, but it's a little tiny bigger than 1. And then water is much bigger than that. So I don't know the exact number here, but we can know that the index of refraction is higher. And we know that water is more dense than air. So because of this, we know that the speed, so if we had a higher N, that means we have a lower speed. So in water, the speed would be slower than air because the N, the index of refraction, is higher than it is for air. So water's index of refraction is higher than air's index of refraction, and that decreases the speed. So it'll end up refracting to something like so. So the angle will change, but the speed will also change. So when light beam emerges from water to air, there is a change in the speed of light as moving from denser to rarer. So rarer is just a term used for a medium where the speed of light moves slower, or kind of like a less dense medium. So the average speed of light increases. So rare where a speed of light is faster. So less dense means faster speed. So average speed of light increases. This is the property of light, and when it enters the denser medium, its speed decreases, and when it moves out of the denser material to rare materials, its speed increases. So this is the correct explanation. So correct answer, great job. This was question number 9. Okay, so on to the next question. Sorry, I'm having trouble with the whiteboard here. It's not updating that fast, so just bear with me here. Okay, so question is asking, increasing the mass attached to a spring will increase the angular frequency of its vibration. So this is kind of giving us, if we had some system with a spring and some mass m, so does increasing the mass of the object at the end of the string increase the angular frequency of its vibration? So the equation for angular frequency for a spring system is W, which is angular frequency, K, which is the spring constant, over m, which is the mass, square rooted. So we can see here that if we increase the mass of the object, we would actually get, so because the mass is in the denominator, if we increase the mass, this would actually lower the angular frequency based on this equation right here. So this would be false. So the answer here is false. So this is kind of the equation for simple harmonic motion. So the mass m is attached to a spring.